Hello again. This is the last segment of a rather long week, I have to admit, but it has hopefully been an informative one. In danger of stating the obvious, improved restoration results can be obtained when the restoration filter takes the local content of the image into account. The filter, in other words, is not content agnostic anymore. This should make sense conceptually, but it is also strongly supported by experimental evidence. So based, for example, on the local spatial activity, a different restoration filter is applied to each and every pixel. In this segment, we describe one way to introduce the spatial adaptivity of the restoration filter with the use of weighted norms. We discuss one specific way to adjust these weights based on properties of the human visual system. We introduce spatially adaptive restoration algorithms in terms of their iterative implementation, since now direct solutions, for example in the frequency domain, are not feasible anymore, but more importantly because the spatial activity of the image needs to be computed from the available data. Since such data are noisy and blurred, it makes sense conceptually to estimate such activity at each iteration step based on the partially restored image. We also include in this segment an example of the effectiveness of the positivity constraint in restoring an impulsive signal. We also address the problem of the so-called ringing artifacts, which appear in restored images, especially with certain types of blurs, such as the blur due to motion between the camera and the scene. Developing image processing algorithms which are not content agnostic, but instead take the content of the image into account, and therefore performing a different filtering processing operation per pixel, is of the utmost importance in image processing. It has been proven that such filters outperform non-adaptive, non-spatially adaptive filters in all applications that they have been considered. We actually showed a spatially adaptive noise smoothing filter when we talked about enhancement, and we would like to do the same here when that we're talking about image restoration. So one of the ways to introduce spatial adaptivity for the constraint least squares filter is to consider this function phi of f that we want to find its roots, that is equal to what's shown here. So I have the fidelity to the data term again and the smoothness constraint that we talked about, but though these norms are weighted by a W1 weight and a W2 weight here. So let's see first how the weight should be interpreted. So if I have a weighted norm of x by W squared, this is simply x transpose W transpose Wx, and can also be written as the sum one, let's say there are capital N elements in the matrix X, W of I squared, Xi squared. So here W is a diagonal matrix with entries W1, W2, Wn in this particular example. So we see that the weights assign different importance to the elements of X. So now when I find the norm, the contribution of each element in X is not the same, but again it's weighted by the value of Wi, and the Wi's are all non-negative. So with this then definition, if you wish, of the weighted norm, we should be able to find the gradient with respect to f of the terms inside the parenthesis. It's something we did before without the weights a couple of times already. And if we do so, the successive approximations based iteration is shown here. So this is the iterative algorithm that I'm performing now. If W1 equals W2 equals identity, then this is exactly the constraint least squares iteration that we have talked about. I should comment here that this iteration cannot be taken out to the discrete frequency domain even when H and C are block circulant, simply because the weight matrices W1, W2 are not block circulant, and therefore I cannot take it to the discrete frequency domain. So in implementing this iteration, I could either implement it in the spatial domain or alternate between spatial and frequency domain. The convolutions are performed in the discrete frequency domain, and then we take the result back to the spatial domain to implement the weights and go back and forth that way. What are some of the choices of these weights? One possible choice is shown here, drawing from some experiments that were done to demonstrate the masking properties of the human visual system. According to it, high frequency information in the image masks high frequency noise, and put it differently, the noise is not as visible at the edges as in the flat regions in an image. Therefore, when we perform restoration, we can allow noise go through at the edges, and the way to accomplish this is by setting the entries of the W matrix here very small, close to 0 at the edge locations, and allow them to be larger at the flat region. So if W is small, then we disable the smoothness constraint, and that's what we want to do at the edges. So this visibility matrix is calculated according to a formula like this. It's made proportional, or rather it's made inversely proportional to the local variance of the image, sigma squared of f. So at the edges the local variance is high, therefore V, therefore W is small, therefore C of f is disabled. We can then choose W1 as 1 minus W2, because we want with that term to kind of do the reverse. So we want to perform deconvolution at the edges, and we don't enforce that much deconvolution in the flat regions. Actually, if I have a perfectly flat part of the image, then blurring it will not change anything. It will be exactly the same signal. So this is just one choice of W1, W2. People have experimented with all kind of other different choices, but the concept when it comes to the convolution that we are discussing here is, again, to not perform smoothing at the edges. Therefore, sharp edges will be restored, and they'll be noisy, but that's fine. The noise will not be visible, while we want to smooth out the noise in the flat regions. Now, a question is, how do we calculate the V here, for example, the local activity? All we have available is Y, which is a noisy image. So we can work with that and try to remove noise and then find the local activity. Or alternatively, we can update these matrices as the iteration progresses. So in other words, we can make these matrices functions of K. So I could put a K here in all the weights, which again, all this means is that at each iteration I apply my estimation of the local variance, and then the visibility function, and then W1, whatever the formula is to update these matrices. So let's see now how this filter performs in restoring an image. So here is one implementation of the spatially adaptive CLS filter that I just mentioned. So this is the noisy blurred image we've been working with. This is the adaptively restored image. This is the CLS image. That both are implemented in an iterative fashion. By comparing the two, we see that there's a finer control between noise amplification and sharpness in the adaptively restored image. The edges are considerably well restored, while the noise has been suppressed. In the CLS image, we don't have this control. The edges are sharp, but there's a lot of noise amplification. Here we show the visibility function computed by finding the local variance in the image. It's like an edge detector, so black are the small values, so at the edges the weight for the smoothness term is small, therefore the smoothness term is disabled, and it's high values, white values in the flat regions. And here finally we show the difference, the absolute difference between the two restorations, the spatially adaptive and the non-spatially adaptive. We see that they differ at the edges, which is also something we can visually confirm, but also there is a lot of noise in the difference, which is the noise that we see amplified in the CLS restoration. Actually, both the visibility function and this difference are mapped in the 32 to 255 range linearly for visualization purposes. So the spatial adaptive filter is a rather powerful framework, you might say, but its success depends on the appropriate choice of those W1, W2 matrices. They can be done once at the beginning, or they can also be updated as the iteration progresses. Of course, there's the issue of proving the convergence of the algorithm when the weights are updated, but there is work in that direction as well. You try to linearize this nonlinear function, you try to optimize, and there are some convergence results as well. We want to demonstrate here with a simple example that the positivity constraint that we mentioned earlier can be a powerful constraint when it comes to restoration. So here is a toy one-dimensional signal. It consists of 3 impulses. It is blurred by this 1D motion blur over 8 samples that we have been using, and this is the observation. Clearly, since these 2 impulses are close together, they are not distinguishable anymore after blurring. And also the intensities here, the values rather, are small because the motion blur is normalized. If I run the iterative least squares algorithm with the positivity constraint, which means that at each iteration step, the negative values of the restored signal are set to 0, are clipped, then I'm able to obtain a perfect restoration, perfect recovery of the 3 impulses as shown here. If I run the iterative least squares without the positivity constraint, then this is the result we obtain. The 3 impulses are still picked out, but their height is not the correct one, and then clearly there's a lot of activity in the rest of the signal that should have been equal to 0. It should also be clear that applying the positivity constraint at the end, after the algorithm converges to a result like this, is not the same as applying it at each iteration step, because clearly here, if I set the negative values equal to 0 at this signal, I'm not going to obtain this signal. You recall that in a number of restoration examples we showed, these so-called ringing artifacts are present. So an edge here, a sharp edge, propagates, as shown here, for example. So you see a couple of artificial, non-existing edges. If we look at these images and measure this distance between these replications of the edges, these are equal to 8 pixels, which is the length of the degradation, the motion blur, and as expected, the ringing artifacts are a function, should be a function of the impulse response of the degradation system. So here is a simple analysis of what takes place. Hij is the impulse response of the degradation system, Rij the impulse response of the restoration filter, their convolution, we call it S-all, and in essence, S-all is convolved with the original image to give us the restored image. So if things were ideal, then H should be the convolutional inverse of R, and therefore S-all should be just a delta. If we take this to the frequency domain, then S-all UV should be equal to 1. So the ringing artifacts are due to the fact that there are deviations from the delta, as we'll see in a simple example next. So for the degradation we've been using throughout this presentation, 1D motion blur over 8 pixels, we show here the frequency response of the overall system when direct inversion is used. So I can match in the restoration filter exactly the inverse of all frequency values of the frequency response of the degradation, except at the locations of the zeros, since the inverse filter is 0 at those locations as well. I perform here a generalized inverse. So this frequency response is 1 at all frequencies except the exact zeros. If I take this signal now to the spatial domain, I obtain this. It's a delta almost equal to 1 here, but we also see we have this train of smaller impulses that are 8 pixels away. So as already mentioned, it's this impulse response that will convolve the original image to give us an estimate of the original image. So if I'm 8 pixels away from an edge, I will find the exact value of the intensity of the image at that location. However, I will have a replica of the edge due to this little impulse. If I move 16 pixels away, I'll have a second replica due to the second impulse, and so on. The good news, you might say, is that these impulses are small, and therefore the ringing artifacts will not be really pronounced. The bad news, of course, is that such a direct inversion amplifies noise. So if we look now at the frequency response of the overall system when a least squares filter is performed iteratively, here is what we see. It's exactly 0 at the zeros of the sinc function. However, close to those frequencies, we see that the values are not exactly equal to 1, because as we mentioned, the values of those frequencies close to 0, they will not be fully restored, will not be equal to the direct inverse, since also there's a low rate of convergence towards the inverse filter at those frequency locations. So if I take this back to the spatial domain, I see this picture. So the impulse is not exactly at 1 now, but also this train of impulses I had before, it tapers off, but the values of these impulses close to the big impulse are now larger. Again, the spacing is 8 pixels. So if I convolve now this impulse response with the original image, I do see that 8 pixels away from an edge, I will have a pronounced edge due to this impulse. 16 pixels, I will have another replica due to this impulse, and after 2 or 3 impulses, the ringing artifacts will fade out, and this is exactly what we observed in the image I showed in the previous slide. So with the iterative least squares filter here, we deviate from the delta, or deviate from 1 here, and this gives rise to ringing artifacts, but at the same time, this way we can control the noise amplification. So there's this important engineering trade-off that takes place when I compare the various filters. So we reached the midpoint of the course. You just completed 50% of the material. My warmest congratulations to all of you. During this 6th week, we learned that the recovery problems encountered in practice, which come with different names such as restoration, super resolution, and punch sharpening, are all inverse problems. We had actually discussed in detail another inverse problem, that of motion estimation, earlier in class during week 4. We established the notation for being able to represent images as vectors and the degradation equation in matrix vector form. This representation allows us to model and provide restoration solutions to a larger class of problems than the restoration deconvolution problem. It provides us also with the flexibility of utilizing a number of optimization techniques from the literature. We then discussed 3 widely used approaches for solving the image restoration problem. The simplest possible one is the least squares approach, also referred to as inverse filtering. The extension of least squares is constrained least squares, with which prior knowledge about the solution is incorporated into the solution process. This is also an application of the theory of regularization. Finally, a general framework was also presented, the set theoretic estimation approach, which is applicable to solving various other recovery problems in addition to the restoration problem. This is, of course, the case with the other methods we discussed, such as least squares and constrained least squares. A specific synthetic image example was used throughout the presentation so as to easily demonstrate the relative advantages and shortcomings of each method. As you saw, the topic of recovery is rather mathematical, drawing material from linear algebra, estimation theory, optimization, etc. Again, even if not all the derivations and algorithmic details are crystal clear to you, you still can have some good basic understanding of the approaches and be able to make immediate use of them in your work and study environments. Although equipped with the knowledge you acquired this week, you should be able to provide a solution to any inverse problem. We will continue next week on the same topic, since it is a rich and important one. So, see you next week.